So hello everyone, welcome to day 11, 2 questions of physics per day series. Here we are going to solve 2 questions. The first question says that consider a particle described by the wave function given by this particular expression where psi as a function of x and t is exponential iota kx minus omega t. The first question says that is this wave function an eigenfunction corresponding to any dynamical variable or variables, and uh, if this statement is true, then you are required to name them. The second question says that does this represent a ground state? The third one says that obtain the probability current density of this function. So great, let us try to debunk that. This is the introduction where we are required to ascertain three things. Okay, so let us try to consider the action of momentum operator. Okay, where we know that momentum operator is minus iota h bar t by dx. Okay, so when you operate that particular wave function with this momentum operator, you are going to get h bar k and then the wave function itself. That means this h bar k is the eigenvalue. This h bar k is eigenvalue, and obviously that is the eigenvector. Okay, so you know that if you take any general operator O, okay, and you operate it on any wave function psi, and you get some constant c times the wave function psi itself. If this is the relation, okay, then this is what we call that psi is eigenfunction. O operator is any dynamical variable, also known as operator. Okay, here in this case, in for this particular question, the momentum operator is that operator. Therefore, we can say that psi is an eigenfunction of the momentum operator with eigenvalue h bar k. Now you are required to do the same thing with energy operator as well, which we call Hamiltonian for a free particle. And whenever the particle is free, you should know that the potential is zero in that region. That is why the particle is free. Okay, in that case, you should know that the operator of energy, okay, energy operator is iota h bar d by dt. So you should know the difference in between momentum operator and energy operator. Here, when you again operate the energy operator on psi, you get some constant and the wave function itself. So again, using the same logic, if this is the case, then we can say that okay, this psi was the eigenfunction. This c, that is here h bar omega, is the eigenvalue, and obviously the corresponding dynamical variable operator is energy operator, which is Hamiltonian. So again, you can say that psi is also an eigenfunction of the energy operator with eigenvalue h bar omega. Now we know that energy for any bound state is negative. So here energy eigenvalue is greater than 0. That is, it is h bar omega, and which is the positive quantity, which obviously corresponds to a free particle and not a bound state, because for the free particle the energy is greater than 0. Okay, so in that case we can conclude that the wave function will not represent a ground state or any bound state, because ground state is a kind of bound state. The particle has to be in the ground state. Invariably means the particle is in bounded energy state. For example, you can check the basic hydrogen atom, that it is given by minus 13.6 electron volt n square. You take in whatever the n is, in each and every case the electron is in bound state, and that is why the energy is negative. Now next you are required to find the probability current density. Okay, so it is actually the density of the flow of probability across the region. So probability current density is denoted by a small j as a vector, and it is h bar 2 mi and this expression. Here we have the complex conjugate. This is complex conjugate, and this is the obviously derivative or gradient of the gradient of the wave function. In this case, you are just required to find the gradient or derivative of the complex conjugate of the given wave function and the wave function itself. So here we have the complex conjugate where we replace iota with minus iota. So in that way, when you find, you are going to get the derivative of psi, which is iota k exponential iota within the bracket kx minus omega t. Similarly, you can move forward for the derivative of complex conjugate of uh, given wave function, which is minus iota k exponential minus iota kx minus omega t in the bracket. So now you have all the ingredient to find the probability current density. You are just required to put it down just by finding the terms within the bracket. So within the bracket, you can see that the first term within the bracket is going to be iota k and the second term is minus iota k, and they are in subtraction, so that once they are going to get added, and finally you are going to get the constant probability current density. Okay, so we have all the three conclusion here for each three question, that psi x is an eigenfunction of both the momentum and energy operator with eigenvalue h bar k and h bar omega respectively. It does not represent a bound state or ground state since the energy is positive and the probability current density is h bar k divided by m. Now, can we measure the kinetic and potential energies of the particles simultaneously with arbitrary precision? The question simply asks you that you are required to find the kinetic energy and potential energy at the same time. That is why they are using the word simultaneously. And arbitrary precision means that precision should be in your control. They are not going to be controlled by some kind of mathematical formula or mathematical equality, inequality, whatever. So you know that in the quantum mechanics, the answer to such question depends on whether the corresponding operators does commute or not. If the corresponding operators does commute, then you have one simple answer that okay, if they are commuting, that is any operator A and operator B are commuting, then they can be uh, measured or observed with infinite or arbitrary precision at the same moment. So let us try to find if they are commuting or not. So we have the operator formulation of kinetic energy, which is given by this. Okay. So you know how we find that kinetic energy in such case is always P a square upon 2m. And now you have the momentum operator. You have the momentum operator minus iota h bar dy dx. Okay. So in 3D it is simply minus iota h bar and del operator. Okay, so what you are going to do, you are going to multiply it, so when square it and divide it by 2m to get the kinetic energy. So whenever you are squaring it, so minus 1 minus will become plus and iota square will be minus 1 and h bar will be h bar square and this will be del square divided by 2m. So this is what we are calling kinetic energy operator. And we know that potential energy operator is the potential itself. So to determine if simultaneous precise measurement is possible, we can compute the commutator as we have discussed. So this is the commutator, and you know that this commutator is actually described like if you want to find the commutator of A and B, then you are required to write it AB minus BA. So at first operator A is operating on B and then second operator B is operating on A, and we are taking the difference. Okay, and this is what, if you get 0, then we can say that okay, we can measure both of them at the same time. So we are doing it. Let's operator act on the arbitrary wave function psi. Okay, so in that way, this is the commutation, and this is operating on any generic arbitrary wave function. And obviously this is easy to do, that it is going to be h bar square upon 2m del s square, and then within the bracket the potential operator being operated on the our arbitrary wave function psi. And similarly here, the potential comes to the left, and at first it is being operated on the by the kinetic energy operator. So you can notice here that we are just using this formulation. We have two operator A and B, and it is actually AB minus BA. This is what we have done. So you are required to apply the Laplacian to the product. Okay, so we can see that here we can apply that. Okay, this is the basic identity which you should remember. If you don't remember the identity, then you will have to calculate it in the examination hall itself, and it would be time consuming. So this is the identity, that you first take out the side to the left, then del S square V, then 2 times del V times del psi, and then V on the left side, and this time del S square psi. Okay, so you can see the interrelationship. It is true for any such case. Now you are required to substitute this in the commutator. So you just found this particular expression, and then you are required to put this whole expression in place of that. So when you do it, you get that okay, the commutation is actually not cancelling the terms, and the term is not 0, so it is non-zero in general. Therefore the kinetic and potential energy operator do not commute, and if they are not commuting, then you cannot measure them simultaneously. The same happens with the position and momentum operator as well, that position and momentum operator do not commute as well. You can try it yourself, that you have the position and the momentum operator. Okay, so you know that it is minus iota h bar d by dx. If you try to find the commutation by operating it on any generic wave function, then you will find that okay, this is also not commuting, that is not coming to 0. That is why they cannot be measured simultaneously with arbitrary precision, and for that reason we have the Heisenberg uncertainty principle, where we have delta x multiplied by delta p x greater than or equal to h bar by 2. Okay, so this is the reason. Okay, you cannot measure it arbitrarily with arbitrary position, and that means they are bound by some equation, that okay, you can see the precision in x is inversely proportional to precision in momentum in the same direction. So we can say that since the operators do not commute, the uncertainty principle implies that both kinetic and potential energies cannot be measured simultaneously with arbitrary precision. However, in a special case where we have this as constant or linear in coordinates, so that this becomes 0. So in that case, we can say that commutation is possible and simultaneous measurement becomes a reality. Okay, so in general, simultaneous measurement of kinetic and potential energy with arbitrary precision is not possible because the operators do not commute. Precise simultaneous measurement is only possible when this is constant or linear in coordinates. Great. So let us move forward. Okay, this was end of it.